All right. Welcome everyone to another video. Today we're going to be talking about trig substitution in our kind of this series of looking at these different methods of integration. We started out with integration by parts and we talked about trig integration, which in terms of just kind of working with your trig functions to kind of use identities to switch things around or rewrite it in a form that's better. So now we've come across something called trig substitution today. And what trig substitution is, we'll get to, but I'd like to start off first with a quick example. Okay, so let's say that I gave this problem and asked you to evaluate it. Would you know how to do it? Let you think about it for a sec. But the answer is yes, we would. Because if I let u be 1 minus x squared in this case, and I let du be negative 2x dx, right? We would have everything we need to be able to do u sub here and make this a very, very easy integral to work out. However, what if this x was not here and I instead just had the integral of the square root of 1 minus x squared? What would I do in this case? Well, I would have to, I could, actually, I'm not sure what I have to do at this point, right? I guess that's kind of the problem, right? So you could try to do integration by parts on it, which if we made, u equal to this thing and then dv be dx, then maybe we'd get an x out of it and things would work out. But that still may not give us exactly what we want. And dealing with the square root, we might still run into some issues. So you can feel free to try it if you want, but we may not advise that for now. There's no trig like functions at the moment that we can just kind of move around or switch around, right? So then our last remaining option, as for now, is maybe this one you just read right up here, trig substitution, right? Now what that means, why I would even consider using that here, right? Let's think back to a quick trig identity, which is if I take sine squared x and add cosine squared x to it, that is 1. And maybe, so we're not confused, I'll put theta here instead. Okay. So this is an identity that we learn, where we just take, if I take sine n squared and cosine n squared, that leaves me with the number 1, which is very nice, right? It comes from our Pythagorean identity and just kind of relates my two functions together into this one beautiful identity. Now, what would happen if, for example, I took this identity and I subtracted sine squared from those things? Well, that's going to leave me with cosine squared theta equals 1 minus sine squared theta. Just like that. Okay. So here's the question for us. What if I took this expression, the 1 minus x squared here, and I let x be equal to the sine of theta? What would happen? Well, let's think about it, right? So I can't just put sine theta in, of course. I'm also going to substitute something for this dx, which I can just easily say if I just plug something in for x, then dx is just going to be the derivative, which would be cosine in this case. And by the way, this may look weird at first, right? What we're doing at the moment. But this is sort of like maybe an inverse, what the book calls like an inverse substitution of sorts. We're still substituting, but instead of saying u equals 1 minus x squared and then getting du and working from there, what's happening is I am not saying u is some function of x. I'm letting x itself be something. And so then everywhere where there's an x, I can easily replace it with x, this x or this dx part, right? So what's going to happen once I take these things and I plug them in is I'm going to be left with the integral of the square root of 1 minus sine squared theta, and then times cosine theta d theta. Okay, good. Fantastic. Okay, but what is 1 minus sine squared theta? Well, that's cosine squared, right? So I'm going to get the integral of the square root of cosine squared theta times cosine theta. Well, look at that, right? What's going to happen? Square root of cosine squared is cosine, so I'm simply just left with the integral of cosine squared theta d theta. Do we know how to integrate this? Absolutely. We have to use a little bit of maybe to substitute this real fast with the identity we have. Remember from 7.2 that we established that cosine squared theta is also equal to, besides this guy here, of course, is equal to 1 plus cosine of 2 theta all divided by 2. Right? So, and the reason we do that is so we can get a trig function of 1 degree and put that in place of the squared, right? Because the squared is a little bit harder to work with since it's even. So we're going to let this be equal to the integral. And notice it's divided by 2, so we'll take that 2 and bring it out as 1/2 times the integral of 1 plus cosine 2 theta d theta, which is going to be the integral of 1/2 theta. Now, what's the integral of cosine? Well, integral of cosine is sine, right? And since I had this 2 inside, I had this discussion again in 7.2. If you need to review it or anything, just let me know, or you're unsure, then just talk to me. But we're going to get 1/2 times 1/2 sine 2 theta, right? So I'll write over here real fast. The integral of cosine 2 theta is d theta is 1/2 sine 2 theta, right? 1/2, maybe I'll make some more room here, equals 1/2 sine 2 theta, right? Because I just do the integral normally, but then divide by the number on the inside. So I get 1/2 times 1/2, which is 1/4 sine 2 theta, and then plus c. Okay, so that is our integration done, right? So now we've done the integral, right? Am I done at this point? Well, no, because I didn't start with this, right? I started with this expression. So I need to fix this, right, and make this work somehow. Okay, so feel free to kind of take down whatever you need there. I'm going to erase it fast. Okay, but we'll just kind of remember what we found so far. So we start off with the integral of the square root of 1 minus x squared dx, and we've said x, it needs to be sine theta. If x is sine theta, which makes dx cosine theta d theta, then we get that this is the integral. Then the integral evaluates to 1/2 theta plus 1/4 sine 2 theta plus c. But we need to take it back in terms of x, right? So at this point, we should be thinking something very similar to what we've done, maybe what we worked with when we talked about the inverse trig functions, right? In terms of finding what each of the sides are, how to figure out what the values are going to be. And so we're going to apply that here, right? So first, let's start with this theta. We want 1/2 times theta, and we want to put theta in terms of x, right? Well, we know x is equal to sine theta, right? So that's the same thing as saying that theta is equal to the sine inverse of x, right? You take the sine inverse of both sides, or you relate it to the inverse, but we get this, right? So that theta is going to become sine inverse of x. Now, that doesn't necessarily help us here at the moment, but it at least gives us this piece. Okay, next. When it comes to sine 2 theta, right, I can't really work out sine of 2 sine inverse x at the moment. So instead, I'm probably going to have to use my double angle identity to expand that. And if you remember, sine 2 theta is equal to 2 sine theta cosine theta. So then this piece, so again, we have 1/2, and that's going to be sine inverse x. And then sine 2 theta becomes 2 sine theta cosine theta, which gives me 1/2 sine theta cosine theta. Now, we know that sine theta is equal to x, right? So this term right here is going to become x. But what about cosine? Well, if I'm unsure of what cosine is going to do, right? Here, let me make that a little bigger. Make sure you can see it. So we know that sine theta is going to become x, right? Now we want to understand what's going to happen with this cosine theta, right? But if I know sine of some angle equals x, right? I want to know what the cosine of that same angle is, which of course is sine inverse x. I can make a triangle, right? Specifically a right triangle. Here's my right angle, and here's my angle, my theta. Okay. And I know that the sine of theta equals x, or maybe in this case, I'll say it's x over 1, right? Now, why is that relevant to us? If the sine of theta is equal to x over 1, then that means that I can take that and apply it to this triangle. So I can take x, right? Because sine is the same thing as opposite over hypotenuse, correct? So x relates to the opposite side, and and 1 relates to the hypotenuse. So then, if I want to find this last side to give me cosine, I simply just need to take the Pythagorean theorem, which will give me the square root of 1 minus x squared. Okay, fantastic. So cosine theta, remember, is going to be adjacent over hypotenuse, but that's just the square root of 1 minus x squared over 1. So in the end, our final answer is going to be 1/2 sine inverse of x plus 1/2 x times the square root of 1 minus x squared plus c. Okay, can't forget about the plus c's, of course, but that'll be our final answer. Okay, so we'll see some like different examples later on as we're working through, and we'll again kind of talk through those more. But here is kind of our first example here of what this trig substitution is all about. Okay, also we'll be able to have like a more structured kind of a easy way to understand the steps to take and where to go from here. Okay, like how to know what to do in each scenario. And so I'm going to present that now. Okay, so let's do it. Whenever I'm using trig substitution, I always should be using some sort of radical or something like to the 1/2 power. Maybe it's 3/2 or 5/2. It doesn't matter. I'm just going to write each one with the radical. Okay, so we have 3 cases. The first case is if I have, just like in this last problem, if I have a squared minus x squared. So in the one I had, it was 1 minus x squared, but I'm going to make it more general to just have a in general. So it's really anything. And if I have the square root of a squared minus x squared, but that's on the top and bottom, wherever it is, then I should use the trig substitution. X equals a sine theta. Why? Well, if I take that and I plug it in, right, I would get the square root of a squared minus a squared sine squared theta, which would give me the square root of a squared times 1 minus sine squared theta. Right, because I can just factor a squared out of both of those. But then the a is going to come out, and I'm just left with the square root of 1 minus sine squared, which is cosine squared. But that would just give me just like that. Okay, so that's why we would use a sine theta rather than just sine theta, right? To get that rid of that a in there. Okay, now remember, a doesn't have to be a perfect square. Usually it is in these examples to make it nicer, but it doesn't have to be. Okay. Now, the next case is going to be if I have, maybe I'll write it the other way, a squared plus x squared, or x squared plus a squared, it doesn't matter. Now, if I have this, then the trig substitution I need to use is x equals a times tangent theta, okay? Now, why is that? Well, let's think about it. Again, that a is just, it's going to be brought out of the radical, and I'm going to be left with 1 plus tangent squared theta. What is 1 plus tangent squared theta? Why, it's secant squared theta, or tangent squared plus 1, whichever way you think about it. But in either case, it's going to be secant, and I can find the square root of secant, so I can have this. Okay, good. So if I have this in my problem, I have a radical and it looks like this, then I should use x as a tan theta to do my substitution. Okay, last. If I have x squared minus a squared, then I'm going to use the function x equals a secant theta. Okay, reason being, the a is going to come out again, and just like we had 1 plus tangent squared theta equals secant squared theta, I also have from the same formula that if I subtract 1 from both sides, that secant squared minus 1 is tangent squared. So if I put secant in here, I'm going to get tangent right after I take the square root, allow me to work this out. Okay, so these are the 3 cases we need to keep track of that we're going to practice with today. And so that's how you kind of look for it. Okay, so nothing, again, not really too bad. I mean, the problems might be tedious themselves, but to figure out which one, it's going to be pretty straightforward. Okay, so yeah, if you see a radical in a problem, good chance you're probably going to have to use trig substitution, right? And it's going to be one of these 3 forms. Okay, awesome. Well, let's go ahead and do another example. So that first example was just like a, let's think about it. Let's kind of talk through it. But now let's get into our real example number 1. Okay, so this is going to be the integral of the square root of 9 minus x squared over x squared dx. Fantastic. Okay. So what do we notice here? Well, there's our square root, right? And so I have 9 minus x squared, right? Now, again, hopefully you wrote down those 3 cases. Which one of those 3 does this fit into? Well, it's going to fit into the case where x equals a sine theta, right? Because we have a number minus x squared, which is exactly what we want. And in this case, our number is 9, which is the same, which is our a squared in this case, right? So if a squared is 9, then that means a is going to be 3. So I'm going to choose a to be 3 sine theta in this case. Again, that'll allow me to bring out this 9 to give me the 1 minus sine squared that I need. Okay, now I don't just replace x, right? I also have to place dx. So we're going to find what dx is. So dx is going to be 3 times cosine theta dθ. Okay, so now let's take that and let's put it in here. So we're going to be left with the integral of square root of 9 minus x squared, which is going to be 9 sine squared over 9 sine squared theta, because there's x squared down here, times 3 cosine theta d theta. But this is going to be the integral of, now we have 9 that comes, I can factor out of both of these terms. Square root of 9 is 3. So I'm going to get 3 times the square root of 1 minus sine squared theta over 9 sine squared theta times 3 cosine theta d theta. Good. Now notice we have 3 and 3 and over 9. 3 times 3 is 9. So all of these constants are going to cancel each other out. The square root of 1 minus sine squared is cosine squared. So we're just left with cosine. So we have cosine times cosine over sine times sine, which is going to leave us with the integral of cosine squared over sine squared d theta, which is equal to cotangent squared theta. Okay, now, do we know how to integrate cotangent squared theta? Unfortunately not. You could try to play around with it a little bit, and do another sort of substitution if you want to try, but that's the easiest thing for sure is to remember another one of our identities, right? So we have 3 major Pythagorean identities. The first is sine squared theta plus cosine squared theta equals 1. The second is tangent squared theta plus 1 equals secant squared theta. And the last one, which doesn't get brought up as much, but is still relevant, is that 1 plus cotangent squared theta equals cosecant squared theta. Again, it doesn't matter what order. I feel like the reason they write it this way is just how they get it in each type, but it doesn't matter if you have the 1 first here or the cotangent squared first here, it doesn't matter. Okay, but 1 plus cotangent squared is equal to cosecant squared, right? More importantly, cotangent squared theta is equal to cosecant squared theta minus 1, which is great. Okay, reason being, I can rewrite this, right, as the integral of cosecant squared theta minus 1 d theta. Okay, good. So again, we just want to use a trig identity. I noticed it was a square, so that's the first place to go to. It's pretty easy with the tangents, secants, and cosecants, cotangents if there's a squared. If we have sine or cosine squared, it's a little harder, but this case I can just use an identity to rewrite it. Okay, now we know the integrals of both of these, right? The integral of cosecant is actually negative cotangent, not negative cotangent squared, negative cotangent just by itself. And the integral of 1 is theta, right? So once we have that, once we kind of rewrote it, right? And again, you might want to just kind of think through that, remember some of your identities to make sure you understand it. I can fully integrate that, okay? So let's take this and I'm gonna make some room up here. I'll leave kind of my substitutions, but we'll bring up this result, okay? So our integral, after we make our substitutions, the solution is going to become negative cotangent theta minus theta plus c. Okay, but obviously I started with x, so I would rather have that in here instead, right? Similar to last time, I have a theta term, so I can simply just take x equals 3 sine theta and solve it for theta, right? Because I can take x over 3 equals sine theta, just divided 3 for both sides, and then taking the sine inverse, I get that theta equals sine inverse of x over 3. Okay, so that part's good. But now what is the cotangent of theta, right? Well, to do that, we can use what I just wrote here. Maybe I'll make it a little bigger just to highlight it. So we have x over 3 equals sine theta. We can use this fact that also is about theta to construct the triangle, right? So let's make a right triangle again. Here's my theta right here. And then we know that the sine of theta is x over 3. Sine is opposite over hypotenuse, right? So I'm going to get opposite over hypotenuse. Now, just like last time, we can figure out what the opposite side is by using Pythagorean theorem. And when you use Pythagorean theorem, you're going to find that this is the square root of 9 minus x squared. Okay, good. Now, what is the cotangent of the triangle, right? That's what we need to think about. It's going to be pretty easy, hopefully, for us to remember what the tangent is at least, right? The tangent, right? Tangent of a triangle is opposite over adjacent, right? Which would be x over the square root of 9 minus x squared in this case. But for this problem, right, we want cotangent, right? But that would just be the opposite of tangent, or adjacent over opposite. Okay, so in the end, we are going to see that our answer is going to become the cotangent of negative cotangent of this triangle, which is going to be negative the square root of 9 minus x squared over x minus theta, where we found theta is sine inverse of x over 3 plus c. And this is our final answer. Okay, good. So pretty similar to the last one, a little bit more maybe, having to use our identities in the middle, but otherwise same exact process. And all these are the same exact process. It's just having to remember some identities and how to work things out. Okay, great. Let's do a couple more examples and we'll be done with this. Okay, so next we're going to tackle another problem. And this will be example number 2 in our case. And we're going to take the integral of 1 over x squared times the square root of x squared plus 4 dx. Okay, good. Now what do we notice? Well, we have x squared plus 4. We have a radical, right? We have the square root, so it might be useful for us to use trig as trig substitution, right? And what is my substitution going to be in this case? Again, look at the list. Which one does it match? Well, it's going to match x is the tangent theta case. And what should a be in this case? Well, a match is, so this 4 is supposed to be what my a squared is. But a squared is 4, so a is going to be 2. So I get 2 tan theta. Okay, we need to find dx. Dx is going to be 2. What's the derivative of tangent? Well, it's going to be secant squared theta d theta. Awesome. And then I'm going to take this, I'm going to plug it in. So we're going to get the integral of 1 over x squared, which is going to be 4 tangent squared theta, times the square root of 4 tangent squared theta plus 4, and then times secant squared theta d theta. Okay, but 2 secant squared theta d theta. Okay, now let's go ahead and do another step. So these 4 will factor out to the outside. The square root of 4 is 2, so we'll get 1 over 8 tangent squared theta, right? 4 times 2 times the square root of tangent squared theta plus 1, and then this is times 2 secant squared theta d theta. But notice we have 2 over 8, which is going to simplify to 1 over 4, and I can take that constant to the outside. So that's great. So we have 1/4 here. Also, tangent squared theta plus 1 is secant squared theta, and the square root of secant squared is secant. So I'm left with the integral 1/4 times the integral of secant squared theta over tangent squared theta times secant theta d theta. Okay, now what's going to happen is 1 secant is going to cancel out, right? I don't see anything at the moment, so maybe we'll write everything in terms of, maybe kind of flip things around, see if we can write this in terms of sine and cosine and get something. So I'm going to get 1/4 integral of 1 over cosine theta over sine squared theta, right? Because it's tangent squared. So sine squared over cosine squared d theta, which is going to give me 1/4 times the integral. So we have 1 over cosine theta times cosine squared theta over sine squared theta d theta. Well, 1 cosine is going to go away, leaving us 1/4 times the integral of cosine theta over sine squared theta d theta. And we have this. Okay, so hopefully you can kind of follow along. Again, I said I don't know what to do here, so let me just write everything in terms of sine and cosine, and so I get this. So I'm running out of room. Let's take that and let's bring it up real fast. Okay, 1/4 cosine over sine squared. Okay, so we have, so this is equal to 1/4 times the integral of cosine theta over sine squared theta d theta. Do I know how to integrate this? Absolutely. This is actually a Calc 1 integral that we should know how to do, right? Now, why do I say that? Well, let's kind of think through it, right? We have cosine and we have sine, right? What's going to happen here if I let u be equal to sine theta? Well, du is going to be cosine theta d theta. but that's exactly what I have, right? And so I'm going to get 1/4 times the integral of du over u squared, like that, right? So this is the same as this if I use this u substitution, which this integral is the same thing as 1/4 integral of u to the negative second power du, right? So again, I just brought it up as u to the negative second power, which we know how to integrate using power rule, right? Or kind of our integration power rule in a way. So we get 1/4 times, now remember with the integral power rule, we do u to the -2 plus 1 over -2 plus 1. Now we'll plus c, of course. And then we're going to get 1/4 times, or -1/4, right? Because -2 plus 1 is -1. So we get -1/4, and then u to the -1 is the same thing as just u in the denominator. So I get -1/4u plus c, but that's the same thing as -1/4u, which is sine theta c. Okay, great. So now that I have -1/4 sine theta, is there anything else I can do here? Well, absolutely, right? I know x is equal to 2 tan theta, right? I want to get back to x, so let me use that. So x is 2 tan theta, which is the same thing as tan theta is x over 2, right? And I can use this to make a triangle out of it, right? So I have a triangle where, right, tangents opposite over adjacent. So my opposite side is going to be x, and my adjacent side is going to be 2. Using Pythagorean theorem, we can get the hypotenuse, which is going to be the square root of x squared plus 4. And then the sine of this triangle is opposite over hypotenuse, which is going to be x over the square root of x squared plus 4 in this case. I'm going to take that, I'm going to plug it in. So we're going to get -1/4 times x over the square root of x squared plus 4 plus c. But then keep change flip that. I'm going to be left with negative square root of x squared plus 4 all over 4x plus c. Just like that. Okay, so you can see that, make sure it kind of looks odd. This should be a plus, right? Same things right here. What we're left with, this is our final answer, which is exactly correct. Okay, there we go. So another example. Hopefully that all makes sense. Hopefully you kind of were able to work through that and get to the same answer. Good. Okay, awesome. So like I said, we had 2 more to do. We're going to have 1 more, and we're going to call this video good. In this example, it's going to wrap up, kind of take 2 different concepts in one. We're going to look at example number 3, which is one of my own creation, which is going to be the integral of 1 over the square root of x squared plus 2x dx. Okay, so you might look at this and you might say, okay, I see a radical, okay, and I see x squared plus something, so that must mean that I need to use tangent. But that's not quite the case, right? Because this isn't 2, it's 2x. That's kind of an issue, right? I might want to use trig integration or trig substitution on this, right? But I can't because I have x squared plus 2x right now. I don't have x squared plus plus a number, right? So what I would like to happen, and even if it's not maybe just x in particular, is I need to get something squared plus a number or minus a number or something in here that's going to make this work. It's going to make sense of this, right? So To do this, we need to bring back our good friend, completing the square. Okay, so if we remember, right, if I had x squared plus bx, and maybe even have like a plus c term of some sort, right? So plus c, right? If I wanted to take this thing and rewrite it, right, so that I had x plus something squared plus something else, what I would do is I would take that b term and I would divide it by 2, and then I would square it, okay? And once I found that, I would want to add that term, which would be b squared over 4, and subtract it. Now, why is that? Well, because I would get x squared plus bx plus b squared over 4 plus c minus b squared over 4. But this is a perfect square, this guy, which would give me x plus b over 2 squared plus c minus b squared over 4. Now notice that x term, that just instead of having x squared and x, that x term by itself is gone now. Everything's just kind of within the squared now. So I have a x squared or x plus something squared plus a constant, which is exactly what I want to happen here. So we're going to do that in this case, right? Now, as I said, we want to take this term, right, our x term, and we want to divide it by 2, which would be 1, and then we want to square it, which is also just 1, right? So this one's a pretty simple example, but still a good explanation of what's happening, right? So what's going to happen when I take the square root, right? Or I'll just take the thing inside the square root and add 1 and subtract 1 from it. This is a perfect square now, right? So this is the same thing as x plus 1 squared minus 1. Now this looks a lot more like what I would need here, which is fantastic. So I'm going to take this. This is the same thing as x squared plus 2x, right? I'm going to replace that with this, put it in there, and then we're going to work this out, right? So, and I just established using completing the square that this integral is the same thing as 1 over the square root of x plus 1 squared minus 1. And then that's all times dx. Okay, now this looks a lot better. This looks a lot more like what I want for this problem, right? Maybe I'm going to make it a little darker so we can see it still. Okay, so we have the integral of 1 over square root of x plus 1 squared minus 1 dx. So maybe that's a little better. Okay. Now I can use trig substitution here, right? Pretty easily. But instead of just x equals something, I'm going to use, notice, I'm going to take whatever the thing is that's being squared. So instead of using x now, I'm going to use x plus 1. So I'm going to let x plus 1 be equal to secant theta, right? Now, why is that again? Remember, we had 3 cases. In the third case, if we had x or x plus something squared minus a squared, then I needed to use secant. Now, since it's just 1, a is going to be 1, so I just use secant here. Okay, awesome. Now, when I find the derivative, right, the derivative of 1 is 0, so that doesn't affect anything. So I'm going to have dx equals, and then what's the derivative of secant? Well, it's going to be secant theta tangent theta d theta. Just like that. Okay, fantastic. Once I've come to that, right, once I've got to this point, right, I can take this, I'm going to plug it in here. So this integral is going to become the integral of 1 over the square root of secant squared theta minus 1 times secant theta tangent theta, and then can't forget about the d theta down here. Okay, but the square root of secant squared minus 1, well, we know what that is. That's going to be the square root of tangent squared, which is just tangent. So we get the integral of secant theta tangent theta over tangent theta d theta. Cross out the tangents, and we're left with the integral of secant theta d theta. Okay, now remember, we found this one in 7.2, right? We should know it. Maybe it's one you want to memorize. But this is going to be the natural log of secant theta plus tangent theta plus c. Okay, now again, we're not done. We need to make sure to plug in, properly what we have. We know secant's x plus 1. We don't know what tangent is, but that's okay because we'll pull out the triangle. Right, here's theta, and here's a right angle like that. Okay, now we know secant is x plus 1, right? Which, if you don't remember cosine is the inverse of secant, or the reciprocal, I should say. And cosine is adjacent over hypotenuse. So what that means is that secant is the hypotenuse over the adjacent. And what that means is that my hypotenuse should be x plus 1, right? Maybe x plus 1 over 1 is the best way to write this. And my adjacent side is going to be 1. Now, again, using Pythagorean theorem, I can get the last side, which is going to be the square root of x plus 1 squared minus 1. Or if you want to rewrite it, right, as we did at the beginning, that's the same thing as x squared plus 2x, right? Because those are both equal. It was harder to see in this case, but in this case, it's a lot easier to work with. Okay, now tangent, right, of my triangle is opposite over adjacent. Adjacent is 1, luckily, so it's just square root of x squared plus 2x. So our final answer is going to be the natural log of x plus 1, right, because that's secant. X plus 1 is secant, plus the square root of tangent, which is going to be that as square root of x squared plus 2x plus c. That's our final. Okay, great. Well, that's all I have for today. Hopefully you've learned from this and understand it and are able to kind of practice with it and work through it. Thank you for watching. Thank you for taking the time to look through it. Let me know if you have any further questions, and I hope that you have a great rest of your day. Thanks.